Okay, so we talk about another algebraic structure, ring. So far we have discussed group and we have discussed several properties of the groups. So, it was having only one composition. So, we are dealing with this group is under group is a algebraic structure under the composition star. I mean there was only one composition. Now, suppose we have two compositions, two binary compositions. Say we have a set R. This is a general sense, this is ring. So, we denote this set by R. This is not necessarily a set of real number, that set. This is any set R, any non-empty set R, and we have two operators star and say another operator say rho. For simplicity, we take this R, one operator in the additive sense and another operator in multiplicative sense for simplicity. But if you like general notation, we can very well use the star and another this small o. Okay. But anyway, we want to make our life simple. So, we just take this operator as plus and dot, additive sense, multiplicative sense. But these are not the real number addition or complex number addition. These are any two binary composition. We take any two binary composition, and for simplicity we are taking this to be additive sense, and this another composition we are representing to be in multiplicative sense. So, star plus and dot. Okay. So, now suppose we have a non-empty set R, which is non-empty. Let R be a non-empty set. Any non-empty set. Okay. And suppose we have two operators star plus binary composition and dot. Okay. If it is closer, then it will be in R, but if it is not closer, then it need not be in R. So, we have two binary composition plus and these are any two binary composition are two binary composition or binary mapping. Okay. This is additive sense, this is multiplicative sense, but these are any operator, any general operator, binary operator. Okay. Now, when we say this algebraic structure, this set along with these two operator will form a ring. We call this will form a ring is said to be a ring if it is satisfying certain property. If it is satisfying certain property. So, what are those properties? So, the first property is if it is satisfying certain property. So, first of all this R and this operator, first operator, this additive sense operator should be an abelian group, is a commutative group, abelian group. Okay. And the second one is with the another composition, the second composition this dot, I mean we are taking this in multiplicative sense for the simplicity. This should be a semi group, and we have two distributed property which is related, which is dealing with both the operator. So, this is R3 rule 3. So, this is A plus B dot C is equal to A dot C plus B dot C, and this is true for all A B C belongs to the set R. Okay. This is called this is called right distributed law, and the left distributed law is A dot B plus C is equal to A dot B plus A dot C, and this is also true for all A B C. Now, if this property is satisfied, then we call this algebraic structure the set R along with this two operator will form a group, form a ring. This algebraic structure is called a ring. So, this is the left distributed law, distributive property or law. Sorry, this is right, because this is the right side operation, and this is left distributed law. Okay. Now, if this is satisfying by a set R along with these two operator, then it is called a ring. This algebraic structure is called a ring if it is satisfying these properties. Okay. So, first of all, this set R has to be abelian group under this operator plus. This set R has to be a semi group under this operator dot, and these two distributed law must satisfy. Okay. So, now this is also having some properties. This abelian group means it must follow 5 properties. If you recall, every group has a 4 property: closure, associativity, existence for identity, and existence for inverse of each element. And along with the for abelian group, commutative group, we need to have a star must be, that plus must be commutative. And the semi group means it has 2 properties: closure and associativity, that will give us a semi group. So, if you write the details of these properties, so basically this will give us how many properties? 8. Let us just write those. So, this is a set R and we have 2 operator plus and this. Now, these are the properties must satisfy. So, A plus B must belongs to R for all A B belongs to R. This is the closure property of the plus, first operator. Second is A plus B plus C must be A plus B plus C. This is true for all A B C belongs to R. This is the associativity property of this plus. Then existence for identity. So, A plus, there must be identity element, we denote this as 0, because we are dealing with additive sense. So, 0 is the representative of the additive identity. It is nothing to do with real number 0, this is just a representation. If you feel, we can use this E plus, this is the identity element for plus. But anyway, for simplicity we denote this by this symbol 0. 0 is just a symbol, it is nothing to do with the real number 0 or complex number 0. It is just to represent, since we have taken our operator is additive sense. So, 0 is just a representation of the identity element in the additive sense. 0 plus A is equal to A, this is for all A belongs to R. This is the existence for additive identity. And then the inverse, every element must have a inverse, additive inverse, additive sense. So, given an element, given an element from A, there must exist a B such that A plus B is equal to B plus A is equal to 0. Okay. So, A plus B, we can write it here such that A plus B is equal to B plus A is equal to 0. So, this is in additive. So, B is the additive inverse of A, usually we denote B by this symbol, because this is in additive sense. So, every element should have inverse. So, this properties is telling us R is a group along with this. R is a group. Now, we want this to be an abelian group. So, we must have a commutative property. So, A plus B must be equal to B plus A. This is true for all A B. Now, up to this is telling us this R is a abelian group, abelian or the commutative group. Okay, these 5 properties will give us R to be a commutative group with the composition plus. Now, we want semi group of the dot. So, this is property number 6. Now, we will talk about properties with this operator. So, it must be closed. So, that means A dot B must belongs to R for all A B. So, this is the closure property of dot, and then 5, 6, 7. Then it must be associativity under this dot. So, that means A dot B dot C is equal to A dot B dot C, and this must be true for all A B C. So, these two will give us a semi group, is a semi group. Okay, these two properties will give us a semi group of R along with this second operator, second composition, and then we have the distributed law. So, this is 7, we have 8. So, left distributed law is basically A dot B plus C is equal to A dot B plus B dot C, and this must true for all A B C. This is the left distributed law, and the right distributed law is basically A plus B dot C is same as A dot C plus B dot C. This is true for all A B C. Okay. So, these two are basically telling us the distributed law. This is dealing with both the operator. So, now if we do B plus C, now B plus C, B is in R, C is in R, and plus is closure. So, B plus C will be an element in R. Now, once this is an element in R, A is an element in R. Now, we can talk about A operate with that other element, and that is by closure property this will be an element in R again. Now, we want this element to be same as this element, because this is again an element in R, because A is an element in R, B is an element in R, then A dot B is an element in R. Similarly, B dot C is an element in R, and plus is closure again. So, this is an element in R. Now, we want this element should be same as this element. So, similar argument here. So, if it's all these properties is satisfying these 9 properties, then we call this is a ring. This algebraic structure along with these two operator is called a ring. So, we have to remember these properties for to be a ring. Okay. So, now we will take some example of a ring. So, before that we talk about commutative ring. Now, we know this plus is already commutative, because this has to be a abelian group. Now, commutative ring means if along with this, if dot is commutative, if A dot B is equal to B dot A for all A B, then this implies dot is commutative, then this is called, this R is called commutative ring. Okay, if all this 9 plus this, if it is commutative ring, then the left distributive law and right distributive law is same, then we have only one distributive law, because they are commutative. So, for commutative ring we have only one distributive law. So, so ring is up to this we have a ring. Now, along with this, if the dot is also commutative, then it is called commutative ring. Okay. So, let me just, and if it is commutative ring, then the left distributed law and right distributed law are same. So, you have only one distributed law. So, this is called commutative ring or so R is called a commutative ring if first of all it has to be a ring, that means all the 9 properties must satisfy, is a ring and it must be commutative in the sense of, because it is already commutative in the sense of plus, and then so and the star must be commutative dot. If these two satisfy, then it is called a commutative ring, and once it is a commutative ring, then the distributed law, left distributed law and right distributed law are same. Okay. So, now we define the ring with identity element. So, we defined a ring with identity element. Okay. So, R plus this. Now, suppose it is a ring. Now, we know that if it is a ring, then R plus is a groove. So, that means there is a identity element under this plus, that is 0. Now, ring with identity element means for ring we do not need to have this existence of the identity for this dot, but if the ID exists, then we say this is a ring with identity element. So, if there is a exists that it is under dot, we denote this by 1, because 0 we are denoting by additive identity. So, this we must denote by so this is same as. So, there must, if there exists a element which is multiplicative identity element such that A operate with this element is same as A, and this is true for all A. Okay. So, since this is your multiplicative sense, so we denote this by that multiplicative identity sense. Otherwise, if you feel we can use this as E1, sorry E dot. Dot is the operator and E is the identity element for this operator, but for the simplicity we can use this notation 1. So, if this is happening, then we can say this is a ring with identity element, then this is a ring with identity element. Ring with identity, if this is happening, then we call this is a ring with identity. If we have a multiplicative identity also, we already have a additive identity, because that is a groove. Now, for multiplicative operator we do not need the identity element to be a ring, but if it is there, then we call this is a ring with identity element. Okay. So, these are all the definition. Now, if it is again commutative, then we say this is a commutative ring with identity element. Now, we will take some example of ring. So, this is the definition of the ring. Okay, some of the examples. Now, if you take Z, set of integer, then plus and dot, this is the real number addition, real number multiplication. This is a ring. Not only ring, this is a commutative ring and also identity element exist other than 0. Okay. Commutative ring other than 0 ID element exists, because commutative ring is okay, because this is a abelian group, no doubt. We have seen this before, abelian group, and also under this dot this is a semi group, and also this dot is commutative. So, this is a commutative ring, but what about the identity? Identity means 1. So, every element, if we 1 is the identity element. So, a dot 1 is equal to 1 dot a is equal to a. Yeah. So, if we take 0 also, yeah. So, this is the, okay. So, for 0 also I was wondering about 0, if a is 0. So, 0 also it is fine, because 0 into a 1 is equal to 1 into 0 is equal to 0. So, that is also okay. So, this is a commutative ring, with identity. This is a commutative ring with identity, existence of identity, that is fine. Okay. Now, another example is the set of all rational number, set of all real number. So, q plus this is also a commutative ring with identity. Now, R, this is also a commutative ring with identity. Now, can you have a ring without identity, commutative ring without identity, like if you take 2z, this is a commutative ring without identity, because identity element for dot is 1, real number 1, which is not here. This is an example of commutative ring without identity, element. Okay. Now, if you take the matrix, say M to R, 2 by 2 matrix. So, this is basically A B C D, where A B C D are coming from R. Now, this, if you take this along with the matrix addition and matrix multiplication, then this is also a ring which is not commutative, because star is not commutative for matrix multiplication, like this dot. This is a ring with identity, because 1 0 0 1 is the identity element which belongs to this set. This is a ring with identity, but not commutative. Okay. We can take other example also. So, now we will define the polynomial ring. So, we define the polynomial ring. Okay, let R be a ring and x is a variable, x is indeterminate, and x is an indeterminate x is an indeterminate. Now, what do we mean by polynomial in x? So, we mean that by a polynomial in x over R, we mean the expression like this. We mean an expression like this: a 0 plus a 1 x plus a 2 x square plus dot 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 a n x to the power n. Okay. This is called a polynomial in x, in the indeterminate x over R. Over R means these coefficients are coming from R. These coefficients are coming from R. So, that is why it is called over R, and this is called a polynomial of degree n, and this is denoted by some p x, small p x, and small p x is this. So, this is a polynomial of degree n over R. Now, we can have another polynomial q x r x. So, we represent the polynomial by this p x q x r x in this way. Okay. So, now we define this r x to be the set of all polynomial over R. This r x to be set of all polynomials over the field, over the ring R, sorry, over the ring R. Now, we define few operation on this R x, like equality, addition and multiplication. When we say two polynomials are equal, when we say so we define the three terms, equality of two polynomial. Okay. And so, equality, addition and multiplication. Equality means if you have two polynomial of same degree, say p x and q x, say a 0, say degree n, and we have another polynomial q x, b 1 plus b 0 plus b 1 x plus dot 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 b n x to the power n. Now, when we say these two polynomial is same, if and only if we say these two polynomial is equal, this is the definition. We are defining the equality of two polynomial. If their corresponding coefficients are same, if a I is equal to b I for all I is equal to 1 to up to n. So, if a 0 is equal to b 0, a 1 equal to b 1, a 2 equal to b 2 like this. So, if the polynomial corresponding coefficients are same, then we say the two polynomial are same. Now, we define the addition of between two polynomials. Addition. Now, suppose you have a polynomial p x of degree n, a n to the power x to the power n, and we have a polynomial q x of degree say m. Now, there are three cases, n is less than m is equal to n is greater than m. So, case 1, if m is equal to n. So, then this p x plus q x is basically summation of a I b I x to the power I is equal to 0 to n, which is same. Okay. So, we are just adding the corresponding coefficient, that is it. Now, if say case 2, if m is, if say n is less than m. So, this is ending before than this. So, then p x plus q x is nothing but say a 0 plus b 0 plus a 1 plus b 1 x dot dot dot. So, n is less. So, that means a n plus b n x to the power n, then after that we do not have term in a. So, then we have only b terms, b n plus 1 x to the power n plus 1 dot 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 b m x to the power n. Okay. Similar way we can define when m equal to m is greater than n. So, idea is to just to add the corresponding coefficient. So, this is the addition. Now, similarly we can define multiplication between two polynomials. Say if we have say two polynomial p x and q x, this is the multiplication. Okay. So, we have two polynomial p x, say a 0 plus a 1 x a n x to the power n, and we have q x b0 plus b1x bn x bm x to the power n. Now, if you multiply means say we are just px plus qx, this is basically another polynomial of degree m plus 1. So, this is basically another polynomial, this is c1 c0 plus c1x up to c m plus n x to the power m plus n. So, we are just doing the product between them, where C I is basically a0 bj plus a1 bj minus 1 dot 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 aj b0, and we are taking the term say a n plus 1, because there is term it is ending up to n. So, a n plus 1 to a m plus n to be 0. Okay. Similarly, b m plus 1 to b m plus n to be 0 also. We are taking these two terms. So, this is the way how we define the multiplication between two polynomial, and then we can show that, and these are all operation basically this operation under this plus and dot. So, in the ring we have two operator plus and dot. So, this all a plus means the first operator of the ring. Okay. So, it is not real number plus, it is in general. If you have a ring with two operator plus and dot, so these are all plus operation in the ring plus operation, and these are all ring second operation, it is in multiplicative sense. Then we can show this R x set of all polynomial with the polynomial addition and this polynomial multiplication is a ring. Okay. This can be easily seen is a ring, and this ring is called a polynomial ring. Thank you.